Okay everyone, today we are going to look at something which is called Archimedes Principle, which for those of you who are excited and keeping along with your textbook, this is sort of 65 to 69 of your textbook. But fundamentally we're going to answer a question. If you throw something into water, something you might remember from year 9 is that things can either float or they can sink. And you probably even, there's common knowledge that if something floats, that means that it is less dense than the density of water. So the density of the object is less than the density of water. And if it sinks, that's because the density of the object here is greater than the density of water. And that has been something that's probably been around in your head since year 9, the first time you measured sort of density and things. Gosh, that's a long time ago. So what the aim of today is to explain where that comes from and to show it. And it arises from Archimedes' Principle, who you might be aware of is someone who, an ancient sort of Greek scientist, and he was able to talk about density, and you had the Eureka cans, and it enabled you to measure the density of irregular objects by immersing them in water. So let's have a very quick recap of GCSE equations. The first two are pretty straightforward. The third one I'm going to just redefine for you so you see where it's come from. And the first is this relationship that we have with density is equal to mass divided by volume. Still the same equation, still fairly straightforward. You will use this a lot throughout this because we might work on the density of things like neutron stars or the density of gases and things. So density is just how much stuff in how much volume, and the symbol for density is a curly looking P. It's called a rho M over a big capital V. Not to be confused with voltage, please. That'd be helpful. I always wonder why people say that. So how do I know if it's voltage or density or volume? It's like, well, what's the question asking you about? The second equation that you might remember is to do with pressure. And again, you met this in year 9, and this idea that pressure is equal to the force over the area. Okay, so it is how concentrated a force is. And so those two equations are sort of these key things. So we get P equals F over A. Somewhat annoying that you've got sort of a curly P for density, a big P for pressure. Sometimes they use a little p for pressure. I tend to use a capital P to try and make sure that I know which one I'm working with. It's not terribly vital either way. And then there was a third equation, which is pressure and depth. Okay, so as you go underwater, so if you go underwater and you go and we have an object, let's say we've got sort of like we've just taken a sort of a flat sort of object and we drop it down some height, what is the pressure someone's updating all the tutor stuff on what is the pressure on this object that's a certain height under the water. And what we're going to say is it's got a cross-sectional area and we're just going to use the symbol A. Okay, so it's got a cross-sectional area, we've taken it underwater. What is the pressure that's exerted on this object? Well, the pressure that's exerted on it is going to come from this column of water that is sitting above it. So this column of water, okay, has a weight, and this column of water is pushing down. So, we want to know what is the weight of the water. So what is the weight of this water? Well, therefore, we need to, if we don't know the weight of the water, we need to know, so the weight equals mass times gravity. The mass of the object, we can use this first thing here. We know the mass is volume times density. So we've got volume times density times gravity. And the volume, well, is your area multiplied by your height, because we're only interested in the area that's sitting above the object. So we've got, so our weight is equal to the height times the area times the density times the gravity. That will tell you the weight of this water, and then we can say that pressure, we use our second one, was that given that pressure is force divided by area, we can say that pressure equals force over area. So that gives us, I'm going to rearrange it slightly because of the way we normally write it, rho G H A over A. So we get rho G H. Now, this is the third equation that you may remember from GCSE, and this is where it's derived from. And it kind of makes sense as you go further and further underwater. If you dive down, H increases, and the pressure you feel also increases. Now, given things can often move up and down underwater, this is sometimes written as a change in pressure is equal to rho G change in height. That may be sometimes the other way that you see it written. But the idea is that as you move up and down, you can get a change in the pressure. Now, you might also notice if you've ever dived down underwater, you can notice fairly rapidly that your ears can start to detect the changes in pressure, and you can start feeling the things. So we can actually say, if we look at, say someone is on the land, and then someone dives into, then you get underwater, and someone dives underwater. What is the, pressure here? And then we can look at water and say, at what point is the pressure underwater due to water the same as the pressure due to the atmosphere? Well, the pressure of 1 atmosphere is 100,000 pascals, 100,000 newtons per square meter. Okay, and that's due to, 100 miles or so of air that's above you. You cannot use this equation for air pressure because the density of air fluctuates and drops dramatically as you go higher. So underwater, it's a fairly good approximation that the density doesn't change. Because it changes slightly due to some forms of temperature differences and the amount of salts dissolved inside them. But generally, it's not changing dramatically. Whereas if you go up a few miles into the atmosphere, the air pressure starts to drop quite dramatically. So that's because of the density of air. So it's not something that we can use as a good approximation for air. But the idea is still the same. It's roughly due, you can work it out from the weight of the air above you. 100,000 pascals pushing down on you. What height do you need underwater to achieve the same amount? Well, we want 100,000 pascals to equal to rho g h. We'll use, for simple things, we'll say that g just equals 10 newtons per newtons per meter, newtons per kilogram. Mixing up my units. G is 10 newtons per kilogram. And we'll say that the density of water is 1,000 kilograms per meters cubed. And so what we end up with here is quite nice. The numbers were all, is that H is equal to 100,000 over 10 times 1,000. So we just get 10 meters. And that's a very startling result, that just simply 10 meters of water is equal to 100 miles or so of atmosphere. It's a real sense of just how much more dense the water is, and sort of consistently dense it is. And it's one of the reasons why you find, even if you dive to the bottom of the swimming pool, you will notice that change in pressure. That extra pressure that's pushing in on you from all directions will have various things. You will feel the push on you. You'll feel it on your ears. You'll feel it on your chest. You'll feel it a lot of places because it's potentially trying to squish you in. So the record for a human free diving, just so you're aware, is 330 meters down, which gives you sort of 3.3 megapascals. So it's quite it's a very, very large distance. Now, just so you're aware, when you dive underwater, this air pressure is still there. Okay, so the total pressure that's exerted on you will always be 100,000 pascals plus, whatever it is that you've got from your pressure due to the liquid, or most normally water. Very few people are diving into mercury. So you would always add them together. It's just that, so if you're 10 meters down, you are experiencing 100,000 from your water, 100,000 from the air. So you're experiencing what we call 2 atmospheres. You go down 20 meters, you're at 3 atmospheres. But because that atmospheric pressure is always there, in terms of calculations, we're often only really interested in the change of pressure. So that's why there's that delta there, is that we're just the atmosphere is always there. So it's then not terribly important. So I want to treat this as a little thought exercise before we move on, which is you might at various points have been snorkeling. And most people who have been snorkeling will have at some point an idea, which is, let's say I want to explore, I want to go exploring on the seabed, and let's imagine that there's sort of like some, there's a box of treasure, yay. T for treasure, they always come from. So there's a box of treasure that's there. Some gold doubloons. I don't know what a doubloon is, but it's there. And let's put a ruby. There's a ruby. So the question is this possible? Can I wander around on the bottom, basically connected to a giant snorkel? Can I do that? What is the maximum height that this very simple setup can take me? Well, what we need to think about is essentially how your lungs work. Your lungs work... Oh no, GCSE biology is approaching. Your lungs work by... there's my wonderful drawing of the lungs. By having the diaphragm pull down, which in turn expands the rib cage and inflates the lungs. And so what you end up with is a lower pressure. Okay, so you end up with the pressure in the lungs becomes lower than the pressure due to the air. And anytime there's a pressure differential, well, that results in air flowing into the lungs to equalize it. Then when you exhale, your diaphragm goes the other way, compresses the size of the lungs, so suddenly you end up with the pressure in the lungs is now greater than the pressure due to the air, which means that what happens at that point is the air will now be forced out. And that is how this works. Now, the pressure differential that your lungs can deal with is largely based on the force that your diaphragm can pull down on in order to expand the lungs. Like, what is the maximum forces that it can do? What is the maximum pressure differential that you can create by taking as deep a breath as you can, by inflating your lungs as much as you can? The biggest pressure differential is around about 0. So the biggest change in pressure that you can create is 0.05 kilopascals. Okay, that is the greatest that you can do. So we can imagine, like, okay, so that's your upper limit. How deep is that? So what we had there is we say, okay, so 0.05 times 100,000 is our biggest amount, is equal to rho g h. So we can get therefore that h is equal to 0.05 times 100,000 over 10 times 1,000. So we have that, cancel that with that, cancel that with that. So we've got 0.05 times 10 to 0.5 meters. That is the limit of the snorkel. You can only go about half a meter down before your lungs your lungs simply are unable to generate a pressure differential. You cannot push against the pressure of the water. So you cannot overcome this external pressure from the water because your lungs are simply not strong enough. There are other problems as well with having a giant tube and trying to breathe through it, in that, you need to not just inhale, exhale, you need to actually clear the air all the way up and to get rid of all the CO2 that you're expelling. Otherwise, you're just going to keep breathing in and out carbon dioxide, and you don't have the strength to do that either. But the idea of marching around on the bottom of the sea with just a snorkel simply doesn't work. And it's actually quite impressive to think that if you had a 1 meter long snorkel, you couldn't use it because you simply do not have the strength to overcome the water pressure, even at a meter deep. And that's why if you see sort of the old diving suits, they were these kind of big pressurized sort of monstrosity sort of equipment, and sort of they have the little grill. And what they are is they are constrained via a compressor that keeps essentially, it mimics air pressure around the body, and there is a compressor unit that forces air down, and then when you need to breathe in and out, what happens is little valves open and you allow air to go in and out. So it's essentially mimicking normal air pressure by putting it down to there, but you have to let the compressed air do the work. You cannot do it yourself, and that's pressure difference. So let's go back to the starting idea of floating and sinking. So, and that comes largely out of this relationship and this equation, okay, this pressure difference, because we derived it by just simply thinking about sort of a dimensionless sort of object, but instead let's put an object with a dimension underneath the water. So we have an object, and this time I'm giving it a set height, and I'm going to give it a height of x. I'm still going to give it this cross-sectional area of A. And what we're interested in is this idea of, is it going to float, is it going to sink? And that's going to be about two forces: the force of weight of the object, which is acting down, counterbalanced against the force of upthrust. And if the upthrust is bigger than the weight, this thing will shoot up towards the surface. If the upthrust is smaller than the weight, it's going to continue to sink. So how do we get the value of the upthrust? Well, what we need to do is to think about the pressure at the top of this box counterbalanced against the pressure at the bottom of this box, because this is a set thing. We are a height h under the water, but our object itself has a height as well. So we can say, we can use our thing, so we can say the pressure at the top is equal to rho g h, okay, which is what we've got. We're ignoring the atmospheric pressure because it's in the case of both. And that leads us to the idea that the force on the top of this box is rho g h a, because force is pressure times area. So we've now got the pressure. This is the force here, and it's acting downwards. We think of the pressure that's on the bottom of the box. Well, this is now rho g h plus x. So what we get there is rho g h plus rho g x, and that gives us a force on the bottom of equal to rho g a, forgot the h, plus rho g h x. Okay, so this little bit here is additional. No, not hx. Ugh, sorry. Rho g x a. Apologies. Too many h's. So this little bit here, this is additional force. Okay, because if we then think about the net force due to the liquid pressure, okay, as the force on the bottom is acting up, the force on the top is acting down. We've got this force and this force. We've got two forces that are the same, so we're just going to be left with this rho g x a is rho g x a. And this is important because this density is, remember, the density is the density of the liquid. X times A is a volume, okay, and G is obviously gravity. So our net, so our upthrust is equal to the density of the liquid times G times the volume of the liquid. Okay? Because the volume of the box and the volume of the liquid that it takes up, they are the same thing. Okay, so this volume here could be the volume of the box, and the volume of the liquid that would have been there that the box has displaced are exactly the same thing. And this is Archimedes' principle. This is what it states. Okay, that the upthrust on an object is equal to the weight of the fluid displaced. Because density times volume is a mass, times gravity, you get the weight, so you get the weight of the fluid. So the more fluid you displace in terms of its weight, the greater the upthrust. And that is why if you've got, say, a balloon and a golf ball, or not a golf ball, but a balloon and a bouncy ball, if they have the same they have the same mass, the same weight, the balloon, because it creates up a greater volume, is going to experience a greater upthrust. It will float. The smaller ball just simply won't. So this is how we get the size of the upthrust. Now what we can do is we can then say, okay, so floating or sinking is going to be about the upthrust, U, against the weight of the object. If the upthrust is greater than the weight, we will float. We're going to start to accelerate upwards. If the upthrust is smaller than the weight, we are going to sink and we're going to go downwards. And we can then see why this is related to density, okay, and this comparison of densities. Because what we can do is we can say the upthrust, which is the weight of the water, is going to equal the density of water times by the volume of the water you've displaced times by gravity. And the weight of the object is going to equal the density of the object times the volume of the object times gravity. But the thing is that gravity, they're both in the same place, so these two things are the same. And the volume of them both is exactly the same. The volume of the object, if the object is 2 cubic meters, it's going to displace a volume of water of 2 cubic meters. So these two things are equal. And so what you end up doing is you're comparing density of water times volume of water times gravity against density of object times volume of object times gravity. And you're trying to work out which one's bigger. Because those four terms are the same, you're really just comparing the densities. If the density of the object is bigger, then the weight of the object will be greater than the upthrust, which means it will sink. So if this is the bigger term, you will sink. However, if this is the bigger term, you will float. And that is how we know whether or not things will float or things that sink, and why it relates to density. And there we go. Hopefully that makes sense. And